If we have an interval from some point A to some point B, and we have a function that's defined on that interval. So we have this function, this is the x-axis, and we want to think about all the ways that we could partition this interval. The partition just means to break up, so we have a set of points that break up that interval. That's our partition P. And what we want to do is to take the width of these little subintervals in the partition, and we're, for whatever reason, multiplying them by the value of the function at some representative point within the interval. If we sum up all of those from the first slice to the last slice, have f at the representative point in the subinterval times the width of the subinterval, then we have what's called a Riemann sum. If we think about all possible partitions and we take the limit as the norm of the partition tends to 0, here by norm of the partition we mean the maximum gap between successive points. So forcing the norm to go to 0 means forcing the maximum gap to go to 0, which means we're forcing all of the gaps to go to 0. Then that's what we mean when we talk about the definite integral of f of x dx. So what we have here is basically we start with a kind of clunky sum, right, where we're adding up these rather blocky intervals, and we're just picking some representative point in each interval to represent the height throughout the interval. So as we slice finer and finer, though, this blocky sum becomes a smooth sum. This is an S for sum, starting at A and going to B of f of x times a tiny width dx. That's what we mean by a definite integral. Now, since an integral is a limit, that limit may or may not exist. We've seen in other cases when we discuss limits, sometimes there was a limit, sometimes there wasn't a limit. So one thing we know is that if our function f is continuous on the interval ab, then we know that the limit will exist. So we know that the integral from a to b of f of x dx will exist. Remember, that's a limit, so limits may or may not exist, but if the function is continuous, we're guaranteed that the integral over that region where it's continuous is going to exist. So now that's a sufficient condition. If we know the function is continuous, then that's sufficient to tell us that it will be integrable, that we can find the limit as the norm of the partition tends to 0. But it's not necessary. There are some functions that are discontinuous and the limit will still exist. For example, you can imagine if we had a function that was cruising along at some constant and then it just had a little jump in it, and we wanted to find the area underneath this curve from A to B. As we slice it up finer and finer and picked our representative points, we might have initially a little bit of trouble, say with that interval that contains the discontinuity. So we might have a little bit of trouble, but as we slice finer and finer, as our slices get finer and finer, that problem is going to be taken care of. So we don't really have to worry too much about a single discontinuity in the function. The limit, as we slice finer and finer, will still give us the correct value for the area under the curve. It will still converge to a particular number. So a function with a single discontinuity in it, it's continuous otherwise, would still be integrable. So just because if it is continuous, we know it's integrable. If it's discontinuous, it may or may not be integrable. Here's an example of a function that is not integrable. So we have an example of a non-integrable function. We take this function and we give it a whole lot of discontinuities. What we'll do is we'll say that the function will be 1 if x is irrational, and it'll be 0 if x is rational. Okay, so we have a function, sometimes this is called the salt and pepper function. If you just look at this function maybe on the interval from 0 to 1, although it's defined for all real numbers, but we have basically the function alternates between having values that are 1 at every irrational number. But every irrational number, if you just truncate its decimal expansion, you can get a rational number that's right next to it. So sort of like salt and pepper that are mixed, and this function just has a lot of values that are 1 and a lot of values right nearby that are 0, and so this function is very discontinuous. And it turns out that this is not integrable. You can kind of see why, because it has to be the limit as the norm of the partition. So you take the sum from I equals 1 to n for each partition, however many slices are in there. You evaluate f at some representative point and multiply it by the thickness of the subinterval. And then you take the limit as you slice finer and finer, so as you do finer and finer partitions. So we have to pick that representative point. So if I always pick a rational representative point, then this sum will always turn out to be 0. On the other hand, if I were to always pick irrational points, then the sum would turn out to be 1, right? Because I would each of my rectangles would have height 1, and so the total area would turn out to be 1. Okay? No matter how fine a slice, if I chose my representatives to be rational, then these would all be 0, and so I'd be summing up a bunch of zeros, which would give me 0 for the answer. But then if I chose my representative points to be irrational ones, if you plug in an irrational point, this function gives you out 1. So I would just get 1 times the length of the interval, which would be 0 and 1. And I could choose a representative, I could choose sort of a blend of irrational and rational representatives, and I could get some number in between. So I could just pick every other partition point, say, to be rational and the other ones to be irrational, and I would get, maybe I could get one half or some other fraction in between. So this function is so discontinuous that the limit doesn't exist. So we have to think about that. But if a function is continuous, we guarantee that it's integrable. If it's continuous everywhere but at maybe a finite, just a jump discontinuity, then there's not going to be any problem either. But we have to watch out for that when we're working with functions. Now, just a little example of this definition. If you look at this, you could compare it to the limit as the norm of the partition tends to 0 of the sum from I equals 1 to n of some function at a representative point times delta xi. So we know that that's the smooth sum from whatever over the interval that we're partitioning. So we're partitioning -1 to 2, so it's the integral from -1 to 2 of f of x dx. So by comparison here, it looks like our function f of ci is ci square root of ci squared plus 1. So this must be the integral from -1 to 2 of x square root of x squared plus 1 dx. Okay, this is actually a handy skill. A lot of times we'll have a problem and we'll want to solve it, but it will be difficult to solve because there's something that's changing throughout the problem. So what we'll do is we'll slice up the interval so that over these short time periods, whatever it was that was changing, so whatever, there's the function that was changing, we slice it up fine enough, then that thing will be approximately constant over a short interval. And so we can solve the problem, or at least approximate the solution, by solving over these short intervals, and then sum up the solutions over those short intervals to get the entire solution if we slice finer and finer and finer. So sometimes we're a little bit sloppy about the notation here. We could use some other letter for the representative, of course, and sometimes we just use the variable itself. So if you saw the limit as the norm of the partition tends to 0 of some sum of maybe xi sine xi delta xi, then if that was the partition of -1 to 2, then you'd get the integral from -1 to 2 of x sine x dx. So we don't stand on a lot of ceremony when it comes to the name of the variable here of integration. The only reason we use the c is that we want to indicate that there's some flexibility in where we would choose our representative point. It could be anywhere in that interval. So you could pick your representative anywhere in this interval of width delta xi, but as the widths of the intervals go to 0, then they'll all be squozen in to a single location, essentially. And so that's why this becomes x.